Okay, so welcome back. I guess we're ready to go now, and so I'm going to start where trying to bind things together, and now we know how to solve dynamic programs and using various methods, successive approximation or value function iterations and the policy iterations. And I'm going to talk about that actually a little bit later. But before we go there, I want to talk about how we actually estimate these models based on microdata. Okay, so we're going to start with this guy. This is Harold Sucker. He used to be the superintendent of maintenance in a bus company, and he'll do optimal replacement of buses. And John, he met Harold Sucker and learned about this guy and got his data and tried to estimate Harold Sucker's deep underlying structural parameters from his optimal decisions recorded in his maintenance record. Okay, so this is all about how to structurally estimate dynamic discrete choice model. Okay, and we're going to start with what John did in 1987 using the so-called nested fixed point algorithm. Now, you guys already know how to calculate fixed point, right? That's what we just talked about. And so now it's going to be a fixed point algorithm. Nested inside an algorithm that's circular parameter space in order to find the optimal parameters that maximize, for example, likelihood. Okay, for every time you value likelihood function, you need to calculate that fixed point. That's why it's called the nested fixed point. Now, a little later, we're going to talk about another way to do this. It's called mathematical programming with equilibrium constraints, where you just impose those fixed point conditions as a constraint optimization problem. You still maximize the likelihood, but you do it subject to constraints of the Bellman equation. And then later, I'll talk about an application of this, but that's going to be tomorrow. So, okay, so this paper from 1987, Russ 1987, not to be confused with Matthias Brooks. He landed in the Red Square in 1987. Okay, so that's my dad's comments. That's what he thinks of Russ 1987. But this is a paper from Metric. Okay, so this is really a path-breaking paper that introduces methodology to estimate these single agent dynamic discrete choice models. And so what John does is, well, he provides its illustrative application that he could actually do it. He could actually learn about how Sucker's deep structural underlying parameters from the data, and then he develops an algorithm that actually allows you to do so with this nested fixed point algorithm. And then, in order to make that tractable, so he formulates a set of assumptions that allows you to solve the model in reasonable time. So I'm going to talk a little bit about some of the challenges that may arise in these sorts of problems. But these assumptions is going to be very helpful. It's going to assume that error aside extreme value, like we heard this morning. We're going to assume additive separability, the utility function, conditional independence. Some assumptions we're going to actually use throughout this week. Okay. And then, well, we estimate the model with maximum likelihood. And use the model to do counterfactuals. Using this micro aggregation of Harold Sucker's individual choices to get a demand function for engines, and sees how with the counterfactual demand for engines depend on the price of an engine or the replacement cost of the engine. Okay, so it's kind of the whole 9 yards. Okay, so who you may think who cares about Harold Sucker and how he's replacing the engine? So, currently, the academic literature cares about it because it's heavily cited, and many of these applied work is actually building on this framework in 2 or more or less degrees. So you have lots of applications for dynamic discrete choices and occupational choice and retirement and brain choice and advertisement. So like a long list. And what I'm going to talk about a little bit later is, you can call this like Harold Sucker on steroids. It's like equilibrium trading in the entire automobile market. So here the consumers, they will choose between different types of cars, between different ages of cars, and they will they will also, choose whether to make a replacement of trading for other cards. So this is like a full range of screen choices. It's not just binary choice. And then there's going to be equilibrium. Okay, and that's much more than this. Okay, so and many of the methods we're going to. So here's just a really non-exhaustive list of methods, but I'm going to start back in 1987 with the nested fixed point algorithm. We're going to hear about Miller talking about this. And Aaron's going to talk about that too, and Dixon's going to talk about the nested two likelihood that kind of sequentially build up new conditional choice probabilities in post-normal structural models to sort of the maximum likelihood as that's true. And then later on, I will talk about the constraint optimization approach, mathematical programming, equilibrium instruments, so much more. Now, I would say that it's kind of conventional in the literature that anyone who proposed a new algorithm that has to do with anything with discrete choice is going to in the sky a picture of us. Because you often use the engine replacement problem as a test bed for whether your new algorithm flies. And if it doesn't solve that, what good is it? So and here's like I like to think of it as a Big Mac index, dynamic structure of the metrics. This is the citation count in this paper, and talking about structural time invariant parameters. I estimated this, and it's not changing over time. It's just the citation count is just following this very parsimonious specification with three parameters, constant control of citation pairs. Anyway, so let's, with that in place.
Singularity.
Yeah, that's right. Singularity is near. Well, I have rejected exponential growth, so this is a polynomial. Okay, so it's just linear growth in the annual number of citations. Okay, so jokes aside. Okay, so let's start formulate the primitives that we need for solving and estimating a dynamic discrete choice model. So we're going to have decision variables. I'm going to repeat a little bit of what you've heard already. And the decision variables D is going to be they're going to be finite here. We'll talk about discrete choices, and they can be in the choice set C. They may be state dependent. So maybe the choice set depends on state. For example, if the state is age, maybe you cannot get children after a certain age, for example, or it could be optimal stopper problem, and state would be whether you're not retired, or the choice that could be limited once you retire. You can't go back and stuff like that. Anyway, so they're going to be state variables. The state variables is going to be the set of variables that describe the relevant information about the model decision process. Okay, so this is all we need to know in order to make optimal choices. We need to know the state variables, and of course, the evolution of it and our preferences. And then there's the instantaneous utility function, or the remote function that we just heard about. And we combine this with time separable utility. We could stay within the confines of this macro-decision process. And the motion rules, well, these are the agent's beliefs about how the state variables evolve through time, conditional on the states and the choices. So I may affect the future evolution of these states by making various decisions. If I go to school, accumulate human capital. If I replace the engine or have a soccer representative, well, next period is going to have a vascular brain unit. So the choices D can affect how the state variable is evolving over time. Okay, and so that's a model. And then given that, we're going to try to see if we can find a solution, or various different representations of the solutions. One would be the value function, which is the maximal attainable utility at a particular state, or it could be the expected value function, integrated value function, or the policy function. But some suggestion specific for the solution is the value function. example. And then, you know, or the pulse function, which is mapping to state space, to action space that returns the ultimate choice. Okay, now that's just a model, and we know how to solve it by dynamic programming. Okay, so the structural estimation, well, what's that? That's we're going to parameterize the model. We're going to say, okay, the utility function depends on parameters. Okay, and it depends, and over and above the station decision, it depends on parameters we want to estimate. Okay, it could be, for example, the parameters of the cost function of Bertel Schjerning. It could be the parameters of utility. And then there's going to be parameters also in the motion rules and state variables. So that's parameters that index how the state variables evolve in conditional online choices and where I'm today in terms of the states. And that could also be parameters in how the choice of the experiences, such as like liquidity constraints or stuff like that. Okay, now given that we've parameterized our model, we want to estimate these parameters, okay, given microdata. So we search for these parameters such that the model fits targeted aspects of the data, for example, like, okay. And that will be data on decisions, states, payoffs. Okay, now, okay, let's go back to Bertel Schjerning, binary choice. Okay. So what we're going to have here, oh, I forgot to, I'm not supposed to point up there. We're going to have a binary choice set, 0 and 1. Okay, so Bertel Schjerning is going to replace the engine, and we're going to index that by d equal to 1. Okay, so that's his active choice. Oh man, okay. Maybe I should turn on sound. Okay, or he just do ordinary regions. So simple binary choice, and then the state variables. That's going to be the mileage since last replacement. I like to think that the cost of maintaining an engine is going to be depending on how old it is or the quality of it. We're going to measure that by the mileage since the last replacement. And then there's going to be some other state variables. We call those epsilons. These are going to be unobserved state variables. And it's going to be one for each of these three choices. So this is going to be a preference shift. The initial preference shifts to inductance in new edges, and that's going to be one for each of the discrete choices. These are epsilons. Okay. With that, we specify the utility function that now depends on the states. Okay, the combined states acts with the mileage. It's going to be observed. The epsilon, the unobserved, this vector of unobserved state variables. And then a decision. Okay. It's going to be like this. So if I just carry on and do no maintenance, just no replacement, then I have to only pay the maintenance cost. Okay, so this is a cost function that depends on the parameter we want to estimate, and it depends on mileage. So this is going to be increasing in the mileage. Older cars, older engines, more expensive to maintain. So we like to think this is increasing. But then if I replace the engine, well, I get a brand new bus. It's good new. So I pay the cost only of a brand new engine that has mileage equal to 0. But then on top of that, I have to pay the replacement cost, RC. Okay, so the parameters we want to estimate here are structural parameters going to be RC and the fail. Okay. Then the state variable process. Well, we can assume here that epsilon is IA with a conditional density here that epsilon that may be conditioned on the current value of x. Okay. Mileage. Well, the mileage since last replacement is going to follow this, what John calls the regulative random walk. And so what happens if you have replacement is that the mileage of the bus today is going to be regenerated to 0. And otherwise, it's just going to drive a stochastic number of miles age period, and that's going to be added to where we were in the. So every time, in every period, the bus rides a little bit. So that's added to the current mileage, unless you replace the engine, and then it's going to be added to zero. Okay, so what we want to estimate is the replacement cost, the parameters of the cost function, and then this parameters in the state position costs. We're going to assume beta is fixed, and the parameters of the distribution of the epsilons it's going to be fixed. So they're going to be either extreme values, so they don't have any parameters we can identify anyway. Okay. So with this decision maker, Parasoka, well, he's facing these choice sets, these state variables, the utility function, and state variable process. And then it's going to do like we just heard. He's going to maximize, make a sequence of actions or time to maximize the expected discounted utility over a potentially infinite horizon. Okay, and this is what we have here. So he's going to try to find it out. Okay, now we also know we can solve this problem by solving the Bellman equation, finding the fixed point of the Bellman operator. Okay, so we got the Bellman operator here. So what did I say here? Yeah, this guy over here, what is that? That's our expected. That's our these expectations here. They're taken with respect conditional on the state variables and the decisions. Okay, so that involves integration. And so it involves integration over the state variables, and there's two types of them. There's both these observed state variables in my equation, and there's also these absolute. So it can be hard to compute this. Yeah.
Oh, there's a question from Zula, and I'll just I answered it, but the question is beta could beta and theta 2 be estimated, or is it just a normalization?
It's going to be hard to identify data without any data on the payoffs, and there is papers on that, and I think this paper by Oystein Daljord and John Bobling that show how you can identify the discount factor by bringing additional information, some exclusive restrictions where you have instruments that affects only the future value but not the current value. And that way you can kind of separate these effects. In finite horizon models, it's going to be easier to identify the discount factor. We're just going to keep it there. Okay, but there's going to be a whole range of potential computational problems here we have to deal with. You know, X state variable is a continuous variable, okay? And epsilon is also a continuous variable, and it's J dimensional. Okay, so you have J dimensional choices. Well, right now J is just 2. If it's about binary choice, you have more choices. It's going to be humongous state. These intervals. This means that the value function itself is potentially high dimensional, and evaluating the expectation up here, though calculating those intervals, all the potential requires high dimensional integration. Now, this is a simple problem, right? But you may have many state variables observed or unobserved. And then evaluating this may require high dimensional interpolation because these are continuous variables. So here it suddenly matters what it is you're approximating, if it's the expected value function, the Q functions, or the value function itself. Okay? Because you don't want to approximate a huge dimensional object. Okay? And then it's not differentiable. So what do we do? So this is where John comes in. Now, we did that in 1987. So we need some assumptions. First of all, you assume additive separability in the preferences. So these epsilon shocks are just being added separable in the utility. Okay. Then second, he assumed that the state variable process obeys conditional independence. Okay, so once you're controlled, for the current value of the state variables, that's really sufficient. Okay, so once you and this is going to rule out a lot of examples. For example, you can't have these epsilons in zero polar, because then that distribution of the epsilons, well, that would have to enter in here. We're going to go a step further and assume epsilon is IDT value distributed. Okay, that gives you a particular functional form for the distribution of the epsilons, and it's going to give us much more. It's going to give us closed form solution for those intervals. So that's the expectation of the max and the choice probabilities, as we kind of alluded to this morning. Okay, so here it is. It's a Bellman equation. So we can do three things. We can separate out the deterministic part of the choice specific value function by the additive separability assumption and the conditional independence. We can reformulate the Bellman equation on a reduced state space, just like we talked about this afternoon. In expected value function space, in integrated value function space, or even in policy space or choice probability space in this case. Or we can then compute the expectation of the max using the probabilities of the expected value, or extreme value distribution. All that together is going to make this problem much more attractive. Okay, so let's just take them one by one. And so here's the Bellman equation. Now I moved a little bit around, and because of the additive separability, we can just move that epsilon to the end. Okay, and this means that we can essentially write the value function here in this simple way, where we have a deterministic part that doesn't depend on the epsilons, and then plus the epsilons, and these are the choice specific value functions. Okay, which is looking like this, which is essentially just the utility plus beta times the expected value conditional on the state of the decision. Okay, so we can kind of separate out these things. Okay, so let's look at the Bellman equation in the expected value function space. Okay, let's just define what it is. It's the expected value function that now depends only on the observed states and the decisions, conditional on the state, and we would take the expectation conditional on the epsilon, on X and the observed states and the decisions. Okay, so we're going to try to integrate out those future states conditional on these two variables. Now, because of the conditional independence assumption, we can express this the state transition, the joint state transition for the two variables X and epsilon by this factorization that we have right here. Okay, so I'm just plugging that in for the state transition process of these two variables. Okay. Now we still have you still have the value function depending on the epsilons, but that's right down here. What does that depend on? Depends on the expected value function. Now you suddenly see you have a mapping from expected value functions to expected value functions plus that epsilon. So we just need to take that integral, that expectation. Okay, so we'll defer that to that a little later, but it turned out that is that's easy to do. Once we assume they are extreme value, we can do it in closed form. Now, this is just like we heard this afternoon. It's still a contraction mapping with a unique fixed point just in the space. So now we can find the expected value function as a fixed point to this Bellman operator in expected value function space. What does it give us? Local value, total conversion for the value function iterations and a point. And this is much lower dimensional. So if you want to say approximate this with splines or neural nets or Chebyshev polynomials or whatever you have, It's just much lower compared to this function.
Is it also smooth, or is that a factor in preferring?
It's smooth. It's smooth. And especially you will see it right away once we have a particular functional form for these epsilons. You're going to see this, it's just going to be a bunch of a log of the sum of a bunch of exponentials that are all smooth functions, which is very, very nice once you're if you want to differentiate it, for example, using the policy iteration, where we take the derivatives of that operator. So we can differentiate it. Okay, so we can also express it in a space you didn't talk about, the integrated value function space, where we essentially just taking one of those intervals. Okay, so we are taking we're taking basically the expectation only with respect to the epsilons, not with respect to x, and just condition on those. Now, so here's the definition. It's just the expectation of the value function taken with respect to the distribution of the epsilons conditional on x. We can do that because we have the conditional independence. Again, here the value function here, you can write that out as the maximum of choices plus those epsilons, then plus and at the additional expectation with respect to the moderate or the absurd state of the place. So magically, if you put this in here, you got a mapping from integrated value functions to integrated value functions. Again, this is also a contraction with a unique fixed point, and we can find the solution with v of I again, and it is even more lower dimensional. It doesn't even depend on the choices. Okay, let's take the third step. Let's see if we can compute those expectations. Now, those expectations can be expressed in closed form once you have the I extreme value issues. And this is going to be other assumptions that deliver closed forms within the generalized extreme value distribution. So you can work with logit and nested logit and to get around some of those unfortunate substitution patterns about the independence of relevance alternatives in the red plus blue plus problem. John talked about this. Okay, but for now, just say that let's just appreciate the beauty of being able to calculate those expectations that involves integrals over this j-dimensional vector of unobserved state variables that we just get by this simple form, the log sum form. And not only that, we get the conditional choice probability that has this closed form logit expression. So these are very convenient because we're going to use them if we want to estimate the model of maximum likelihood. You know, they enter into the likelihood function, the choice probabilities, just like any other discrete choice problem. So that's going to be the expectation with respect to all those epsilons that may be j-dimensional over the indicator function that the observed choice B is actually optimal on the choice that maximize the sum of the epsilon calculation is going to be part of the choice we got overall choice. Well, what's that? That's just the exponential of the twice distinct value function divided by the sum of those exponentials, the logit. Very easy, no integration. So that's a huge benefit. It involves j-dimensional integration over those epsilons. And then on top of this, look at the smoothness we got everywhere. Right? We got the choice probabilities just depend on some exponentials, some smooth functions, exponentials, sums. And the integrated value function, well, that's just a log sum. And the expected value function, if you want to get that, that's just an integral over those log sums. The integrals, it's expectations taken with respect to the state variable process, or the mileage or the sort of state variable process for X. So very very tractable. Okay, so putting all this together, we have now choice probabilities. What do they depend on? Well, they depend on the utility. We can calculate that. We have a parametric functional form for that. So you stick in your X in discrete points, and you can calculate it once you have the parameter vector. You assume you know the functional formula used, so you can calculate that. No fixed point problems or anything. Nothing fancy there, right? Then beta, it's just something we know that we need to have this expected value function, or the integral over the integrated value functions. But we know we can calculate that as a solution to this fixed point equation. So in other words, to calculate the choice probabilities, you need to calculate the fixed point of this Bellman equation here. And then just stick in the fixed point, and you've got the choice probabilities that you need for estimation. Okay. A few words about the state variable process. I said it was continuous. We're going to do the simplest thing. We're going to just discretize this these state variables. Okay, so we're just going to chop mileage into a bunch of bins, 0 to 5,000 miles, 5 to 10,000 miles, 15, and so on. Just discretize it. And that's going to discretize the distribution too, so that we essentially get a macro transition matrix for this discrete macro process. That macro transition matrix is going to be one for each of the discrete choices, one if you replace, one if you keep the engine. And I'm going to show you how it looks like this. Okay, so I'm just trying to visualize this matrix notation. So here's the macro transition matrix for conditional on keeping the engine. Now, if I keep the engine, well, the bus is going to drive every month, regardless of what I'm doing. Okay, so it's going to drive exogenously. And with some probability, it drives so little that we stay in the first interval, and it just move up a bit. Okay, so suppose you're in the range of 0 to 5,000 miles. With some probability, it just doesn't move out of that bit. With some probability pi 1, well, it moves up 1 bit. Probability pi 2, it moves up another bit. At some point, the probability that it kind of moves up several bits is going to be 0. If we have discretized, say, the state variable, say, into like 100 bins or 90 bins, and we go from 0 to 405,000 miles. Well, the last probability out here, that's a probability that I drive 450,000 miles within a month. Okay, so we put 0 probability in that, that's quite sparse. So there's also going to be zeros down here, right? Why is that? Why do you think it's going to be zeros below the diagonal? No, why? That would require the bus to driving backwards, right? And so the language is not increasing. Right? So that's why it's the zeros below the diagonal. Another thing that's kind of current here is that all these pi's are essentially independent of the current state. So how much it drives every period does not really depend on whether it's a brand new bus or whether it's maybe not this example. Let's go up here where we're not truncated. Whether it has been driving several thousand. That's an approximation. Maybe it's not realistic, and you can come up with, it could be that the buses that are older just driven less intensively, and it would have different numbers on the data. In principle, we could estimate the whole thing if we have lots of data, but we just don't have so much data, so we put some parametric restrictions on and just estimate it by 0, 1, and 2. Now that was conditional on just letting Harris circuit relax, no engine replacement. Now, if we replaces the engine, remember that the mileage just becomes zero on that engine when you replace the engine. Then you have this market transition process. So you start from zero, and then the distribution of mileage the following period is going to be the same regardless of the stage you're in. Okay? Because you just regenerated the engine to zero. So these are the traditional conditional. The transition matrix is conditional on replacing the engine. With these transition matrices, we can also write this Bellman equation for the expected value function, or its expected value function space in matrix notation. So all it is that it's this. Remember the expected value function, that was the one that was conditional on discrete choice. We're going to have a vector of expected value functions for each of the discrete choices. Now, each of those you're going to get by multiplying that market transition matrix onto the log sum, and so that's what we have right here. And go again, so we've got to find this vector for each of these discrete choices of expected value function. And this is a vector that we essentially stack them on top of each other for all the different states. Okay, like we've done with the utility functions, the expected value functions, and in this equation here, where it's the integrated value function, we've done it also with the integrated value function. And you've got your transition matrix. So these are just different representations of the same equation, and you can say we're at different places in the loop. Okay, you pre-multiply this equation here below with the conditional transition matrix, while you get the equation above. Okay, we wanted to talk about estimation. Okay, so sure, we have some data on mileage conditions and on replacement decisions. Okay, so we're going to try to do maximum likelihood. So we're going to try to see if we can maximize this likelihood function L with respect to the structural parameters. How does that look like? Well, you got the likelihood by summing all the different time periods for each of the individual buses, both the likelihood contribution for the mileage process. Not going to talk so much about that because this one is the new one, the one that requires dynamic programming. The log of the probability of the observed replacement decisions conditional on the observed mileage. This P here, well, that's our logit formula again. That depends on the expected value function where we need to calculate a fixed point. So I think we have essentially all the bits and pieces to kind of illustrate what the nested fixed point algorithm is. Okay, so we're going to try to see if we can maximize the likelihood function by changing all those structural parameters. Well, in order to do that, well, we need to calculate those choice probabilities, which in turn requires that we calculate the fixed point here. So every time you change the parameters, you've got to change the fixed point. And essentially, that makes the fixed point an implicit function of those structural parameters. And then you throw that back in, calculate the likelihood, move parameters again, and that's the deal. Try to summarize it here. Okay, so since this contraction mapping, whatever, if it's in value function space, integrated value function space, or whatever space it is, it's going to be an implicit, it's going to be indexed by those parameters. I mean, you can see it, right? Right here, parameters, they enter right here, right? So every time you change those parameters, you change the operator, you will change the fixed point. Now, since the operator is a function of the parameters, the fixed point is going to be an implicit function of those parameters. So the nested fixed point algorithm is solving the unconstrained optimization problem, maximizing the likelihood with respect to the parameters by resolving all the fixed point, and again in order to be able to express life. So there's going to be an outer hill climbing element, search over the parameter space. That could be like your favorite quasi-Newton algorithm. I'm going to talk about later and recommend something called the Bertel and Hausman algorithm that use some structure of the problem that in fact we're using maximum likelihood to calculate derivatives or second order derivatives very efficiently by using the information data. But each variation of this requires solving the fixed point. And therefore, it's going to be an inner loop that finds its explicit function by solving the fixed point equation. We can do that by various different methods. We talked about successive approximations or value function iterations this morning. We know it's always going to work because it's a contraction. Okay? We talked about Howard's policy iteration algorithm, which is essentially just Newton's method. And here we call Newton's control iterations, same thing. Okay, so we have various different algorithms, and you better solve this fast if you want to do it again. Okay, now John had data on these 162 buses for monthly recordings of mileage for each of these buses, and then he had data on the replacement decisions. And how do we look? Okay. You can plot the non-parametric passive that's a probability eventual replacement as a function of mileage. Okay, you see here is the non-parametric pattern. It's very figurative. Okay. So estimating, at least with this participation, just by frequency estimator, is going to be with a lot of noise. So it can be good to post. Here's a model you're going to get, or the prediction for a model you're going to get if you just do a simple binary logit model, static version of this model. Okay, just assuming beta was equal to 0, you're going to get that. And here's the model you're going to get from, or the prediction you get from the estimated model we're going to look at this. Okay. So John goes about and estimates all these structural parameters. So here's the replacement cost, and here's the parameter of the cost function. And you can say the relative size of these two things determines how costly it is to repair the engine relative to letting it run another bit. And the estimate model is estimated for various different bus types. There's bus group 1, 2, 3, and 4, and then together. And it's estimated both with beta equals 0.999 and for static model. One of the things that I think we can do here is we can actually test whether these, I mean, given the parametric restriction, we can test whether beta very close to 1, it gives a benefit compared to beta equals to 0, just making a simple likelihood ratio test where you compare the likelihoods of these two models, and it turns out that it's significant. So here's a model ideas. Let's not get too much into the what's with these models. Now, it's going to be discretized at different numbers of grid points, with 90 grid points or 175 grid points. And we can run both of them in the code. We're going to get to that in a second right now. Okay. So here's where it gets practical. There is code on GitHub with a bunch of different, where we have it here, right here. So you'll find the code here, and there's something called Circa MATLAB that has code for estimating the code and the data set for estimating the integral problem using various different. Okay. And so I'm going to run it from my laptop and not from here, but that's where the code is. Okay, let's see if we can find it. see if we can estimate this model. Yeah, it's kind of run bus data. Let's hope it's not too big of a sound. No. We can do it. The code, the main thing here is just to show you, here's the code. You may want to go in and look at what's the implementation of the likelihood function. And,
One of John got to run that fast.
Yeah, no, it didn't run that fast, yeah.
Of course.
yeah. So this is, yeah, it's reasonable fast. You can do it. Anyway, so I'm not going to dwell too much with these results yet. I want to move on to something different. Once you've estimated this model, once you have these structural parameters, you have enough to calculate the implied equilibrium distribution of mileage. And so you can, it's really the product distribution to this macro transition matrix, control transition, with what's probabilities in this case. And that has a product distribution, and we can derive that distribution and figure out what is it, the distribution of mileage in this case. And there's also code to do that. It's called run and for run demand, because it both calculates its equilibrium distribution here and then the demand function. I'm going to talk a little bit about the demand function. So here's the implied demand. You might want to say, okay, why don't we just estimate a static model? You know, static model is so much easier. No dynamic programming. We can probably make that, you know, those transition probabilities in the beginning, we may, you know, make a pretty reasonable fit for where a lot of the action is going on. But the question is, what happens here in the counterfactuals? And you see here, Harold Sucker in this with this demand curve, which is not thinking about the future. It's just much more responsive to the price changes, the price of the engine. We get a very different prediction. You may ask, why don't we just estimate it with a regression? It's just a, you know, it's just a regression line, right? The relationship between the amount of engine replacements against the cost, right? Well, the problem is we don't really have that type of variation in replacement cost. In fact, we don't know what we're trying to estimate. But even if you had, the data you typically have would probably be clustered around in this area, where you have the amount of engine. You don't observe the counterfactual replacement cost. So that's kind of one of the reasons why we want to do structural estimation, because we can learn about something else. We can learn about how Sucker is reacting to those price changes. So estimating the model, then predicting counterfactuals what his demand for engines would be in equilibrium as we change this replacement cost parameter that we've estimated. So I think I said that. Okay, John talked a lot about the pros and cons of doing structural estimations. I'm not going to go to that. I'm going to continue and talk about how you could estimate it with another method. The constraint optimization approach, or the mathematical programming with equilibrium constraints, is also called. Okay, now MPEG, mathematical programming with equilibrium constraints, is used in multiple contexts. It is somewhat general, like you maximize some objective function, like the likelihood function, and then there's some steps of equilibrium conditions that limit these steps. It could be like we've just seen in single agent dynamic discrete choice, where the Bellman equation would be. And so you just formulate this as a constraint optimization problems. Again, instead of maximize the likelihood function, changing those parameters, but also the expected value function, imposing the constraint of the Dolman equation needs to hold. Can also be used in random efficient local demand models. There's also a fixed point problem there. Okay, those of you who know PRP knows we have to solve a fixed point problem. Ruby, Fox, and Sue is also doing that in a very nice paper with constraint optimization, which just imposes that equilibrium constraint. And then we can use it in estimation of games, where you would impose on the Bellman player the Bellman equations of the players would need to be satisfied. So we'll talk about that later. Okay. For now, the Sue and Judd paper, the simplest implementation of the constraint optimization. Okay, so this is just to recap where we were. We have that's the fixed point algorithm that maximizes the likelihood function subject to the parameter zone. Okay. Treating the expected value function as an implicit function of the structural parameters, meaning that every time we change those structural parameters, the fixed point is going to change because we resolve the Bellman equation. So you know that already, how to do that. Now here's another one. It is doing MPEG, maximize the likelihood, subject to the constraint that this Bellman equation needs to hold. Okay, now we're going to have an additional set of variables over and above the structural parameters in the constraint optimization problem, namely the expected value function, the vector of all the expected values in each point of the state space. So if we have the fixed point dimension 175, you have 175 additional parameters. Okay. Now, in principle, since the expected value function is also choice specific, you would have two of those. Okay, but now here there's a little bit of special structure. The expected value being the first state is the same as the expected value for replacing the engine. So we just have one column to remake things a little bit. Okay, but in principle, this is a vector that depends on the number of points in the state space and the number of decisions. So if you want to do MPEG, it suddenly matters for the size of this constraint implementation problem if you were doing it in expected value function space or in the integrated value space. It doesn't depend on the because that made the constraint optimization problem smaller if you're searching over a small space. Now, what they're doing in Sue and Judd is that they're considering various different implementations and highlighting the importance of exploiting viscosity patterns and supplying first and second order derivatives and using professional software, just like you advocated for this morning. Why not just use software that's done by professionals to solve the constraint optimization problem? Okay, because there's a good chance that I'm going to make it better. I think that's a good point. Anyway, so they have two implementations. One they call MPEG Ample. Ample is kind of a high-level programming language, a little bit like GAMS. Those of you who knows about general equilibrium modeling in macro, they use GAMS. Ample is very much like that. You just specify a bunch of equations at a high level, and that formulates the problem, the equations. The mathematical problem, and you pass it to some sort of solver like Nitro or ConOp or SNOp or whatever all these solvers. And that's possible to do it at a high level. It gives you automatic differentiation, just like jazz. But if I understand correctly, you get automatic differentiation. Okay, so you don't have to bother code those derivatives. And I'm talking from experience. I use hours and hours debugging the derivatives. In fact, yeah, I think I could have written twice as many papers, but not to do that myself. Even though I kind of enjoy doing it. So automatic differentiation, that's really a big thing. And then it also discovers these sparsity patterns automatically, like you saw the transition matrix that's very sparse. So Ample is discovering these kind of things. So the bottom line, this is going to be highly efficient. And then there's a MATLAB implementation, because we also want to do something for our MATLAB guys. Well, here you need to find the Jacobian and the Jacobian of the constraints, the Hessian of the likelihood, the sparsity patterns manually, but you can do it. And then there is some software to do the link. Anyway, so different implementation matters. Okay, one key factor for implementation, or two key factors for efficient implementation, is provide those derivatives analytically. And if you think about the size of this optimization problem, I mean, 175 variables, maybe not so much, but it's all very, very small. If you have, say, 100 choices and a million state variables, or states, it's a big problem. Or even if you were to express this constraint level optimization problem in integrated value function space, you only have the states, it's still big. Right? So you want to be very efficient and avoid recalculating the likelihood of the constraints numerically by perturbing each of these different little variables in the constraints optimization problem in order to do those derivatives. It's going to be very expensive. So that's key for implementation. Avoid numerical evaluation of derivatives. And then, of course, exploit sparsity patterns, because the transition equations were sparse. The Jacobian of the constraints, in this case, the Bellman equation, the derivative of the Bellman algorithm, is also going to be sparse, right? It's just a choice probability weighted sum of those transition matrices that I show you right here that were sparse. Okay, these just weighted with the choice probabilities of keeping and replacing. That's what we end up seeing here. This is the sparsity patterns for those Jacobian constraints. At least for the part that has to do with changing the expected values that are variables have shown over here. Then the structural parameters is going to be the first ones we differentiate with respect to. That affects everything. So that's that. The last part is very sparse. And so if you know this is zero, no reason to calculate those derivatives. I'm not going to talk about the second order derivatives, just to talk about my paper right now. Okay, so here these are the transition matrix, right? For keeping and for replacing, so they happen with me. And then you put these two on top of each other, and you get something like this. Okay, because you weight them with the probabilities of replacement. Okay, let's compare. Here's a little Monte Carlo. Okay. And this is from Stu and Joe, the little Monte Carlo they did. Okay, so we get a fixed point dimension of 175. So we just define mileage with one continuous variable into 175 bits. Okay. So that means we have 175 values of the expected value functions we need to find with this constraint optimization approach. Over and above the structural parameters we're trying to estimate, which is going to be theta1, okay, the slope of the cost function, Harris-Sokos cost function, and then the replacement cost. So we're going to try to see if we can estimate those, along with the Mile-Rich process parameters, pi1 up to pi4. These are diagonal elements of these transition matrices. We can, principal estimating these from data. We can also do the full information maximum likelihood, where we have these two parts of the likelihood function. The one that has to do with the discrete choices. If you go back and just remind you guys. Okay, now this guy here with respect to the discrete choices, and then you have the Mile-Rich process likelihood from the mileage cost. So we're going to do the whole thing jointly. You could do a two-step estimation where you just first estimate these mileage parameters, and hold those fixed, and then put that in, estimate the remaining utility parameters. But we're going to do the whole thing jointly. Okay, let's go back. Okay, now since it's Monte Carlo, we need to give the parameters some values, and they use the values that was used in capital 10 in Rust 1987. In fact, the numbers I've just glanced over. So theta 1 is 2, not 2 colon, but 2.457. Okay, and then we've got the replacement cost 11.7. If I remember correctly, these are the estimates for bus group 1, 2, 3. And then we have these numbers here, so you could find these numbers in John's group. And then, given this data generating process, we solve for the expected value, add these true parameters, and stimulate 250 data sets. Or 250 Monte Carlos for 10 years and a monthly data in 50 buses. Okay, so give approximately the same sample size as in John's paper. And then here's a little Monte Carlo comparison. Now we're going to compare the two implementations of MPEG Ample and MPEG MATLAB that doesn't exploit this automatic differentiation and second order derivatives and automatic sparsity patterns. So it's going to be expected to be slower. And you can see it's much lower. 0.13 seconds versus 7 seconds. So implementation of these second order derivatives really matters. Now that was a computed time. Here's another method. It's kind of an older method. It's from 1987, right? So it's not doing that well. It's 24.6 seconds. So it's rather slow. So what's going on? Well, we're counting here the number of major iterations. Number of iterations you do when you do the circle of the parameters. So that's here, okay? And then there's a number of function evaluations. That's the number of times you evaluate the likelihood. But here for NFXP, there's also the number of evaluations of the Bellman algorithm, which is something we need to do because we need to resolve the fixed point here. And that's done 170. Oh, that's not a comment. It's thousands. So it's hundreds, thousands of successive approximations we're doing. And you can see this problem only get worse as we increase beta to 0.939. Well, like we talked about this morning, you're going to have to do many more successive approximations because the rate of conversion of this successive approximation algorithm depends on beta. Right? The closer you get to beta, the slower this algorithm is going to be. We end up doing 748,000 successive approximations to estimate this model, and it took almost 2 minutes. And so I saw this tablet, kind of thought, what's going on? How could John do this in 1987? Okay, so we'll try to do dig in and see what we can improve. And I think actually we already know, right? Because John just talked about this afternoon. Anyway, so here's a little survival guide. Okay, this is not necessarily the death to NFXP. We could do something to improve it. And the main message here is that doing these things that improve computation is important if you don't want to wait for too long. Okay, so first thing is read the documentation manual that's actually out there. So there's a little pocket guide, and I'm going to show you in a second that actually describes everything you can do to improve. And so you have to recenter the logit and log sum formals to avoid some numerical instability. You need to use this fixed point this combined fixed point algorithm that both use the successive approximations and the Newton's method, or the policy iterations, in the best from, and use best from two worlds to improve on the computation of the fixed point. And then, of course, you need to do analytical gradients of the Bellman operator and analytical gradients of the likelihood to avoid repeated numerical calculations of these fixed points and likelihoods, and then use a BHHH algorithm. So here, I'm really just listing like what I found is the most important parts of this documentation manual I'm going to show you. Okay, and you can download it here. I think it's still on John's website. You can get it's version 6. But I'm going to show you a picture of it here. We wrote a little comment on the paper by Super John. Okay, so here's what it says in documentation manual. It says, formally, one can use the nested fixed point algorithm as solving the following constraint optimization problem. Okay, so that's actually what MPEG is doing. Okay, so that's what was in the original documentation. And then he kind of argues why you don't want to do that. Why would you really want to use the structure? The fact that you know that you can solve this fixed point. You have a 4-finite algorithm to solve finite solution. So you can use that and calculate the derivatives of the likelihood by using the implicit function theorems and so on, right? Then you can get a lot of leeway, and so we're going to try to do that. So here's another map of the nested fixed point algorithm. This is the little pocket guide. It's part of the nested fixed point algorithm documentation manual. Print it, and you can just have to do a T4, just hold it a couple of times, right? It fits into the gene, and you can have it with you always. So if it runs cold, slow, here's all the tricks you can do. Let me just give you a brief overview. So here's the inner fixed point algorithm, right? So what you say, okay, you start with the current set of starting values for the expected value function, right? And for the structural parameters, we need starting values, okay? And then for that set of parameters, you do some successive approximation on the Bellman equation. You know, you do that. So you do some successive approximations, and then at some point where you think, okay, now it's kind of close enough to do successive to the fixed point, well, then you switch to the Newton Bertel iterations, doing the policy iterations. Once you get into some sort of domain of attraction. And now every time when you do this, well, here you need the derivatives of the Bellman operator in order to do that Newton's method, right? So once you're done doing that, you have the byproduct of this algorithm, the derivatives you need to calculate the derivatives of the fixed point, which you need in turn for calculating the derivative of the likelihood function and so on. So we're just reusing these components throughout by repeated use of the implicit functions theorem and the chain rule. And that's all you got to do. Anyway, so once you get over here, you can do your Newton step, the Newton Bertel step. So, you know, just everything is here, all the equations are here, just print it out and have it on you. Okay, let's take a few steps. Okay, now first thing you need to make sure is that the formulas you're using are implemented accurately in the computer. Now here's a problem. If V suddenly becomes big, so does the exponential. And it does very quickly. If beta is very close to 1, it means that you are essentially calculating an infinite sum that is very, very puts a lot of weight on all the terms. So V is going to be very big. Or it's going to be big. That makes the exponential very, very big. So you're dividing essentially what ends up being infinity by infinity. You don't know what the choice probability is. The same thing for the log sum. It's just summing a bunch of numbers that are very big. Now that's going to result in numerical overflow, but you can just do a little trick here, just subtract some numbers so all these numbers become negative, and the best number to subtract is the max, because then you essentially you make sure that you don't put in big numbers into this into these exponentials, and these two formulas here are completely equivalent. So that's a little thing that needs to be taken into account. So that reset range is just to avoid numerical instability. Then we want to use the fixed point algorithm that not only uses the successive approximation, but also uses the Newton iterations. Okay, now successive approximations we kind of already know. Here I show it for the expected value, the Bellman equation is expected value from space. So first we're going to do this a little bit. What we heard this morning or this afternoon is that this converges linearly and that it slows down with beta is equal to 1. Okay. Then you can do the Newton iteration, which is this, right? What is this guy? It's the derivative of the Bellman operator. Okay. So you just do a Newton stuff. Now this is quadratic conversion around it. So this means fast once you get near the solution. Here's a little set of successive approximations and illustrations of it. And in fact, you can run this code here. It's called run FXP. I'm going to do only successive approximations. So here in the beginning here, there's a little switch. You can turn off this poly algorithm. And then let's run it. Oh, it's over here. It's called run FXP. It's just solve the fixed point problem for a particular number of iterations. And here's the oh, you can't see what's going on. Let's look at the top. It's taking awful many successive approximations, one for each line. And what I'm plotting here, okay, maybe we want to do a little fewer. Okay, so you can play around with that. Okay, so maybe only 50, right? Or 500. Let's see if we can go to the top. It's over here. Okay, so now we can see it. Okay, so doing some successive approximations. And here's plotting the tolerance. That's the maximum absolute difference between the value of our approximation of the expected value with two successive approximations. Okay. These should be 0, right? Otherwise, it's not a fixed one. What we want to put, what we put in should be equal to what we get. Okay. When we subtract these two numbers, we should pick a 0, and this is the number we have. It's not 0. Okay. What is this number over here? This is the relative size of these two. So this number here is the error bound at iteration 24 divided by the error bound in the previous iteration. And you see here, this is actually the same number all the time. It's equal to beta. So we have the same relative tolerance at all these successive approximations. Did it converge after 500 iterations? Not quite. So we can do better. We can, just give it 500,000. It should converge, or 50,000. Maybe that should be enough. Not quite. Still, we got some tolerance. So why don't we try this Newton's method instead? Okay, and that's right here. What it's doing is it's starting with successive approximations for a few iterations, and then it does the Newton's method. Okay, so let's see how that did. Oh wow, already done. Okay. Made a difference, right? So, and here it is actually, you can really see here the quadratic convergence, right? We essentially, taking the quadratic of the error every time, it's kind of, it's multiplying every time the exponent is moving. You take the log of that error bound, it's a quadratic. Let's go back to the slides. Okay, so here's some observations. First, here's the tolerance. Tolerance always improves. Did we see that? I mean, even though it's not improving a lot, it's still falling all the way down. That's going to be guaranteed because of the contraction. So if you start to see the error bounds suddenly increasing, either you have a bug or it's not a contraction. So that's all right. Okay, but it quickly slows down and declines to be very slow for beta very close to 1. We didn't really try any other values of beta, but you can go in and actually try and play around with these parameters and say change the beta. Say we change beta to 0.9 instead, and see how does that go. Oh, that's the wrong one. Find FXP. We need to do the successive approximations. Did it converge? Well, in 206 iterations, we got a tolerance of 10 to the power of -11. Okay, that's much faster compared to, not having converged after 50,000 iterations. That's because, that algorithm is just much faster when beta is equal to is further away from 0. Let's go back here to the slides. Because here's the overall picture. We change beta. Here's beta equals 0.95. Here's 0.99. Here's kind of increasing values of beta with beta equal to 0.999999 here at the top. And you see when we take the error bound against an iteration count, it's just not smaller. Okay. Now we take the log of that error bound, you see why it's called linear convergence. Okay. And here's the slope of all these lines. It's 0.5 for this guy, where beta is equal to 1. Okay. So you can guess the formula, okay, for the slope of those lines. I'll leave that up to you, the whole math exercise. Okay, what happens if we do Newton? Well, here's a picture. You also saw it when we were running the code. Right? It was first doing some successive approximation, and you get something that looks like quadratic convergence. Only 4 iterations, it just converts to machine precision. Very fast once you're in the domain of attraction. So here you got the iteration count. The first one is just going to be successive approximations, and then you hit the button of Newton, and then you just get 1 iteration, 2, 3, 4 iterations of Newton, and you can see the quadratic pattern in this log of area. Okay, this is what it's called quadratic convergence. And again, this is logically independent of it. Okay, so now, when do we want to switch? How much time? I have like 10 minutes. Yeah. So I suggested we started with successive approximations, or John did in his documentation manual that I read. And then you switch to Newton. When we want to do that? Well, we need to have some kind of theory motivated suggestion. That's what we have. Now, suppose that our initial guess of the expected value, that's where we start our successive approximations, is equal to the fixed point plus a constant k. Okay, so we got nailed the curvature, it's just shifted. Okay. Now, what happens if we do another successive approximation? Let's try to work that out. So here's our initial value. Here's the Bellman operator evaluate, or here's the Bellman operator after 1 iteration. Here's the initial guess on the value function put into the Bellman algorithm. Okay, so the difference here, that's our tolerance at the first guess, after one successful approximation. Okay, so let's just substitute in our guess, which was the true value plus the constant. Okay, so we can do that here. Okay, now this just results in 1 minus beta times a constant. So it's not going to disappear, and it's not going to disappear very quickly when beta is close to 1. Now, what about if we do another iteration? Well, it's going to be beta times 1 minus beta times. But if we divide these two with each other, we get beta. This is exactly what we saw here after a few number of iterations. You see, you get beta. In this case, we had beta 0.90. Before we were doing an awful number of iterations, we got 0.999, right? So it is really, it's a kind of good indication that it's equal to beta. So what does this mean? It means that once you see that the relative tolerance is 0.999 or equal to beta, you have a pretty good idea that you've got the curvature right. But it has this additional constant that is consistent with that. And in that case, if you do Newton, and there's just this irrelevant constant, this is going to be stripped away when you differentiate, and you just get a right solution. So which is why this is a good indication when you want to switch to Newton. So, and that's what the Poli algorithm does. It first does successive approximations until the relative tolerance is close to beta, and then it does the Newton iterations until your admission decision. Okay. Oh, 10 minutes. Are you guys tired? Or you're up for some more? Let's do the analytical derivative of the Bellman algorithm. Okay, actually both needed for MPEG and NFXP. And where do we need that? Well, we need it for the Newton-Kotovich iteration. We also need it if we want to do constraint optimization, because part of the Jacobian of the constraints is exactly equal to the derivatives of those constraints with respect to changes in the expected value. So we can do that. So here, this is needed for the Newton-Kotovich iteration. And it's really, at least in this discretized approximation, it's the n by n matrix partial derivatives with respect to changes in the vector of expected value functions or integrated value functions, where n is the number of points in these. How do you calculate that? Well, that's just beta times the twice probability weighted transition matrices for the states. So in some sense, this is beta times the transition matrix for the control process of both the state variables x and decisions. And that's pretty easy, right? That's just one line of code in MATLAB. So why not just code it up or Python or Julia, whatever you do. And a similar matrix can be computed if you have the expected value function instead. Yeah, so here's a code. In fact, let's just talk about this. This is the Bellman operator implemented in for the bus problem in integrated value function space. So you start calculating the choice specific value functions, depend on the sum of utility, and beta times the expected future result. Since we're getting in the integrated value function, well, we just need to integrate it over the the state variable is X, right? How do we do that? We do that by multiplying the state transition conditional on the choice. And we do that for both of the choices. And so here you get the value of keeping, the value of replacement. Okay. We need to resend the log sum, right? Just like to avoid that numerical overflow problem. So we do that by first calculating the max and then, putting that outside. Then you got your log sum, which is essentially the next value of the integrated value function. That's essentially the Bellman equation for the bus problem in a couple of lines. And then if you want to calculate the choice probabilities, here they are in local form. Here's the key probability. There's a replacement probability as well, which is just 1 minus that. And here are the derivatives, of the Bellman operator. So that's beta times these choice probability weighted sum of transition matrices for the state variables conditional on whatever on each of the two choices, just like we had. And so that's doable. Of course, your problem is going to be much more sophisticated. So, and here it is for the expected value function space. So here's a little bit of detail about how to do derivatives. The basic thing is that really the gradients with respect to utility functions, with respect to utility parameters, is really dissimilar to the static, to the derivative from the static logit model. So it's here you got the indicator for choosing alternative J minus the probability. It's really like a residual, right? This is what you want to put to 0. You want to put the scores to 0. And that has to be orthogonal to the derivatives of the value. So it's like an orthogonality condition. But in order to get these derivatives, well, you need to calculate the derivatives of the utility function, but also the derivatives of the value function, which in turn you can calculate by the use of the implicit function theorem that requires the derivatives of the Bellman operator in the storm. So you can work all these things out, and then you calculate derivatives of the likelihood function analysis. And here's the derivatives of the Bellman operator. So here are all the parts, bits, and pieces that you need for doing maximum likelihood with analytical gradients. And here's the code. Okay. Now, the final thing before I show you the results is just the application for the BAAA. We're just using Newton's method, right? Newton's method is here's where you start. You start with some vector of parameters, okay, and then you make a step. The step is based on the gradient of the function you're trying to maximize times or the inverse of the Hessian. So you need both first and second order derivatives to do Newton's. Now, these guys we know how to calculate analytically, right? We just showed that. But what about these second order derivatives? I mean, it's doable. You can do it, but it's just a lot of work. Okay, and if you want to do it numerically, well, you have to perturb all these scores for each of the structural parameters. So it requires more computation. We want to avoid that. Now, one of the things that Bertel and Hausman suggested was, why don't you use the outer product of the scores as an approximation of the Hessian, since you're doing maximum likelihood, at the true parameters and then over infinity and all that, the information that it is not only, that's exactly what it's saying. Okay. So why not just use that? Then you can just calculate essentially the matrix product of what you've already calculated. Okay, so only first order derivatives are required. It has some benefits. First of all, this guy here is always positive dividend, right? I mean, you take something and square it intuitively, it's not really negative. So this means that you always move in the direction of the top. You almost move in the direction of the gradient. Okay? even in the convex area of the likelihood function, where the second order derivative suddenly changes sign. Okay. Whereas Newton-Raphson is going to move away from the top if you do another iteration. So then it's supposed to do some sort of step halving algorithm where you just have this step every time you see a decrease in the likelihood function. Well, that's not going to help you, right? Because if you look at this graph, it's just going to, maybe your Newton-Raphson step is going to take you out there. Oh, sorry. Oh, out there. But then half the step, well, that's here. Half the step maybe here, but it's just never really going to move you anywhere away from where you start. Okay, of course, it's other good, better line searching algorithm, but the simplest cryptocopulation of step halving in the Bertel-Schjerning algorithm is going to take you to the top of the ladder. Okay, so these are the advantages. It does not rely on second order derivatives, and we always move in towards the top. It's globally convergent to a local maximum for at least for some step halving algorithm, and that's what this businessman who knows about really getting to the top, he would suggest, right? Use B-AAA. Okay, and we do that. It did converge. And as you can see here, the runtime is not 2 minutes like in the Su and Jot comparison. It is only 0.7 seconds to estimate this model. So, implementation matters. You similarly made a little comparison, or, we redid the comparison with MPEG Ample and MPEG MATLAB, and if actually we get a little bit faster, we all have a different computer, and we made some modifications like recentering of the likelihood function that actually make it more robust and a little bit faster. But you see here, essentially, you get the same computer time, so you do the nested fixed point algorithm as you do the others, the MPEG. Having said that, Decker-Steve built very good arguments for doing it the same problem in a different way. If you like to write your code in this high-level constraint optimization software and find that more intuitive, well, maybe it could be a good way to try to solve the model that way. Then we also redid it with a higher sample size. It turns out that MPEG Ample is actually slower because you have to aggregate over a bigger sample size and evaluate the likelihood function many more times, and recalculating that likelihood where you sum over more observations is expensive. Whereas NFXP only really search over 2 parameters, so or 5 in this case, all the structure parameters. So it's not requiring that much computation. Anyway, so I think that's pretty much what I had to say here. And then I think we're going to be ready to talk about Cardinal, an application.